All right, everyone. Thanks for making the time for this session today. I know that there's other interesting session as well happening at the same time. Happy to be here with all of you today. My name is Christian. I work at AWS. I am a specialist compute SA, and basically what I have is that I help customers on try to make an efficient use of their compute workloads. That, of course, as you can imagine, most of my conversations with customers are around Kubernetes. So today I'm gonna cover a few topics around that, and some topics that I'm quite passionate about: performance, autoscaling, and Kubernetes. And before I get started with a lot of the things that I would like to unpack today here in 30 minutes, it's gonna be challenging, but hopefully I can make it and show you not just what is like a mental model, but I want you have a takeaway of a few key points, a few practices that you can actually put in practice if you're using KEDA Karpenter specifically, right? So I will assume that you might have heard about KEDA and Karpenter. I'm not gonna cover kind of like the basics. We had a few sessions yesterday that covered that, so hopefully you made it. Now, let's start with the fundamental problem with when we start talking about performance. The reality is that we have nowadays distributed systems that are complex. We just watched a session before me that was talking about OpenTelemetry and how you can actually instrument your application, how important it is to instrument your application, as well as Whitney was saying at the beginning. And the other topic that is interesting here is that there are too many tools around performance analysis, and every developer, every platform engineer nowadays have a preference of these tools. So along with that, in addition to that, one of the things that people used to think about autoscaling and performance is you're not gonna get, it's basically CPU utilization. And if you look at Brendan Gregg, he's basically an engineer of performance engineering he used to be a performance engineer in Netflix, and he talks a lot about this and saying like CPU utilization is not a good metric, it's basically a saturation metric. And if you start getting into that with autoscaling, usually you start with CPU utilization, and don't get me wrong, at least do something with autoscaling, right? But that might not be the end goal. And what I would like to basically add here, CPU utilization alone is wrong. So maybe we can think about, is there a good metric? Or is there basically a combination of metrics? So sometimes your application might be saying like, CPU utilization is great, memory utilization is great, but your users might be telling you that it's not working. I've been in projects many times where actually all the dashboards were green, or metrics or logs were green, but the reality was that we had a lot of errors, latency was going up. So what I'd like to share with you is basically some mental model. I'm gonna start with that, then I'm gonna go specifically into these tools that I mentioned before. This performance analysis, I'm gonna take the approach that Annapurna Labs have been implementing around these years. If you don't know, Annapurna Labs is basically the startup that we acquired a few years ago, and when we started to create chips, or our own custom chips. If you didn't know, basically we started with creating a lot of one of the first projects that we did on the compute angle was to basically put into the hardware the virtualization. Then we started with networking chips, and then we started with CPU chips. That's basically when it came Graviton. And that team basically runs a mental model of doing this performance analysis. Every time that they deploy or create a new chip, you can imagine that at the scale that they will need to make sure that the chip is gonna be providing the performance that our customers need. So lucky for us, they basically deploy a tool and mental model that is basically applying all of these practices. So if you have time later today or in the future, I will recommend you to give it a look to this performance runbook that this team is actually running every time that they release something into these applications. And basically, I'm gonna cover that tool and how it relates to a Kubernetes ecosystem, because it's basically the context in what we are today. What I really like to think about this is that we change the mindset about, well, the application is not working, the performance that our customers are telling us, it's basically, is being degraded. So instead of going like, saying like, of course, we're gonna go and get the logs and telemetry, but if we're gonna go and test and try to make sure that the performance of the new application is gonna be delivering what we have, maybe we will need to start asking the right questions. So look at this, basically, it says, how does my Java applications throughput on our compute nodes compared to current x86 nodes in my Kubernetes cluster at P99 latency of 10 milliseconds, handling 60% get and 40% put operations? It's a very concrete, it's a very extensive question, but look at what we're doing here. We already know that it's a Java application. We already know that we are gonna be measuring throughput, and we are gonna be comparing two different architectures. But it's not just only that. We're gonna basically say like, hey, what about the P99 latency, that it needs to be, the SLA needs to be on the 10 milliseconds, and this is basically what I'm gonna be doing, or what I will expect my application to do. So that's basically a better question than just saying like, yes, I'm gonna go and send my application and let's see if it performs better. It depends, right? So to answer that question and to help you on making that analysis, let me start giving you a few tools. Now I'm gonna switch into giving you a few recommendations, practical recommendations on what you can start applying. The first thing is that the mental model that I was mentioning before, it's basically, if you go around it, it's very verbose, but with a reason. But you can summarize it in 3 basically steps. Define your benchmark, which is basically something similar to what we did before, and then you have to make sure that you configure your load generator, in this case, if it's a web app, for example, and the system under test, or SUT, which is correlates to what I was saying before. Then do analysis performance. And for this, we have this tool that I was mentioning before that the Annapurna Labs team is using, which is called aperf. This is a tool that I mentioned at the beginning, that we have a lot of tools when we're doing CPU profiling and application profiling as well. So the aim of this tool is basically to provide you a visibility, one single pane, where you can look at these different metrics and you can actually compare. So what I'm gonna show you later on is how you can actually compare this exactly question that I was asking before, how to compare ARM and x86, and what things I can start looking at it, right? So perhaps the very interesting part that I've seen that is becoming more common and common is the CPU flame graphs. So this is basically a project that, again, the same author that I mentioned at the beginning, Brendan Gregg, created a while ago, and it's been popular nowadays, and we can offer that in aperf tool. And the idea is that you know that when you are running test, too many things are gonna be happening, and if you correlate in timeline, the name of the functions, the time that has been taken, it's gonna take a long. So what he did is basically created this tool and aggregated, and you can see in the x-axis the functions, and it's not related on time. It's just basically how much CPU utilization these functions took while you were analyzing, and on the y-axis, it's basically the function that is consuming more CPU. So you can start over at the top saying like, hey, this is basically, and the colors are guiding you onto something like that, right? So we can start talking about this and going deeper. So I would recommend you, if you go and check this link, you're gonna have more detailed explanation of what flame graphs are. So what I want to show you here is basically on my first demo that I have here today. You can see here that the project is open source. You can run it everywhere. You could say that it's cloud agnostic, and even you can run it on-prem. Of course, this started as a tool that you will be running not for a container environment, but we've been working on making it container friendly, because we receive a lot of customers that are asking us for how to profile this type of application on, guess what, on Kubernetes. So what I'm gonna show you here, I have a lot of terminals here. But I'm gonna guide you onto the things that I want to show you. And first, I want to explain what I have, all this kind of mess that I have here. Here you can see here that I have two applications, and one's going to be running on ARM and x86. I have one pod because what I would like to do is to compare apples to apples. And I don't want to, even though I really love KEDA and autoscaling, I don't want to put into the mix more noise, or I just want to make sure that if I run the same test, it will be as similar as possible to the other test, because I want to compare how they behave. And you can see what I'm going to be showing you here is the CPU utilization, because typically what we see customers, and you're not gonna let me lie on this, but typically customers are auto-scaling on CPU utilization when they see 60%, 70% of GCP utilization. And my purpose today is to show you that actually it's fine if you go above that number. It's fine if you actually make an efficient use. Of course, it's gonna depend on your application. I'm not saying that you should look for having 100 CPU utilization. Maybe that's not gonna work in your environment, but when we are doing this type of test, it's actually useful to do that. So what I'm gonna do here is basically use K6, and this is gonna start running a test. And what is gonna happening right now is that a lot of pods are gonna be on pending state. Karpenter is gonna start to launch the node that it needs to run this test. Because remember, what I wanted to do is basically, of course, not run the load test in the same node, right? Even though it's gonna be in the same cluster, which we can argue that maybe that's not isolated at all. But for the purpose of the demo, and if you want to get started, it's a good starting point. So what I'm gonna do here is basically, as soon as the nodes are gonna be running, I'm gonna start. I can see the logs of the application here, and of course, this test is gonna take 3 minutes, 5 minutes to finish, and I don't want us to keep waiting on here. What I'm gonna do basically, just gonna show you that this is running live. And I did a similar test, and I want to show you the results of what the tool is going to generate. So what I'm going to do here, this is basically the logs of the application of the load test. And what I'm going to do here is to run aperf. And you can see here that we're working on doing something like kubectl aperf with a few parameters here. And we basically send the name of the node that we want to analyze, and aperf options, the report name. And what this is gonna do, look at this, it's gonna basically deploy that aperf pod into the node, and it's gonna start to do the performance analysis of what is happening while I'm doing the test. And of course that is gonna be running for 90 seconds, but I have a shorter demo that is gonna run for 15 seconds, simply because what I want to show you is that it's gonna be doing, and I can basically go over here, it's gonna start looking at the nodes that it needs to analyze, then it's gonna deploy the pod, and it noticed that it's an instance type like this, and it's gonna say like, hey, what are the pods that are running in this node, so that I can start analyzing them and actually tie the pods with a process ID, because at the end, it's gonna be a process ID running in the host, right? So remember, aperf is gonna be, or taking the analysis or that telemetry of that information that is emitting, and it's gonna start to collect the data. And you can see here that it's basically working. It's gonna run for 15 seconds. I know it's not too much. And when it's done, it's gonna create a report, and it's gonna generate, it's gonna download it from the Kubernetes cluster to my local machine. It's gonna untar it, and then automatically it's gonna open a new browser with analysis. This might take a while, and I'm gonna take advantage of what I have here. I generated here, by the way, when that tool finishes, it's gonna open automatically here, so I might get interrupted into that. So what I did is basically before I ran the test for 5 minutes, because it's something meaningful. Even 5 minutes might not be enough, but you can run it for longer. And when you compare two tests that you did, I'm calling it x86 ARM, but it could be B1, B2. You can see here how aperf is generating the report. There it is. Here's the live report that it created. So I'm going to stick with this because it's more meaningful and you can see the comparison. I can go here with CPU utilization and I can compare side by side how they are comparing with different perspectives of CPU utilization. So remember that it's not only about CPU utilization load average or 1, 5, 15 minutes, it's beyond that. You can see here, of course, the flame graphs, and you can compare them, and you can see basically the results of, you can analyze here, well, the other analysis finished, and you can compare that, and you can actually reverse, and sometimes, depends on your workload, when you reverse that flame graph, you can actually see very interesting stuff. All right. That's it. That's basically what I wanted to show you with performance analysis and aperf. Let me start talking about what about autoscaling, because one of the premises is that how what we've done before influence that autoscaling part. Because at the end of the day, we want to make sure that it's not only running as we expect it to run, but how do we make sure that when we scale out and when we add more pods or more replicas, we are doing it in the most efficient way. But before going that, when we're talking about autoscaling, there are some trade-offs. And the way that I like to represent this is that with this triangle, where you have cost, performance, and resiliency. Unfortunately, you cannot have them all. So you can go actually check this blog post that I wrote recently, where I go in more detail about it. But you can get the performance that you expected to have. Notice that it might increase the cost. And you can actually been reducing the cost, but notice that the resiliency might affect it. So it's about a balance, it's about a trade-off, and the idea of what I'm gonna start sharing from this onwards is a few practical tips that if you're not today autoscaling effectively, or you're thinking about KEDA or Karpenter, that future, in some future, I hope that these practical tips are gonna be useful for you. So let's cover about the typical scenario that we have with KEDA and Karpenter. Typically, you will see that traffic is stable on the node, and you will start creating a KEDA autoscaling rule that is going to start scaling on the throughput or the request per seconds. This is very traditional, and when the request per second increased, you basically are going to add in more pods. KEDA is basically an abstraction layer on HPA. So even if you are still scaling on CPU utilization, I will highly recommend you to get started with KEDA because you can still scale based on CPU, but you will start getting all these benefits that I'm going to cover. So at some point, the capacity on the cluster is going to be constrained. You have unscheduled pods, and then that's where Karpenter comes in, and it's going to create the nodes that you need. All right, so that's very simple. At some point, you can see here that in terms of efficiency, it's gonna just create the node that it needs, and nothing more, nothing less, depending on your constraints as well. We can, again, we can talk about and cover a lot of things on how to make it more efficient, and again, how to balance between reliability and cost, right? But the reality, all of that sounds good, and maybe you've seen all of those scenarios in very traditional or very introductory sessions about KEDA and Karpenter, but the reality is this. Too many things are gonna be happening when that event comes in, and there are too many variables that come into play. So you have a lot of delays, you have a lot of synchronization that is gonna happen at the same time. So how can you think about it? You're gonna have the delay of getting the metrics. You're gonna have the delay of bootstrapping the node. When you get the node up and running, you have to wait for the node to register. And if you're working right now and deploying AI models or AI-based workloads, you have to wait for the image to be downloaded and so on. So things can get complicated and messy if you don't consider all of these constraints and variants. So we can do better. And hopefully I'm gonna start throwing a few, from now on, start throwing a few tips and recommendations of what I've seen and why I have not seen on many sessions when people start talking about KEDA and Karpenter. So what I'm surprised that not many people talk about KEDA is, of course, the typical example that you have with request per second and SQS or queue-based scaling, and you have basically, you can scale down to 0. However, you can speed up the scaling decisions, and with this configuration, what I'm doing is, because remember what I said before, KEDA works on top of HPA. And what I'm doing here is basically reacting as faster as I can on adding more replicas, and as conservative as I can on removing replicas. Because you might have spikes on traffic and you don't want to be too aggressive on removing the replicas when scaling down. The other interesting thing with KEDA is that, in case you didn't know, you can actually configure multiple triggers. So you can say, like, as I was saying before, maybe it's not about only one metric for scaling. Maybe it's about CPU utilization as well, and memory utilization, request per second, latency, or queue depth, or whichever metric you think it's useful for you. So the first scaler that takes into action is gonna it's gonna run, it's gonna add the replicas that it needs. So basically, you're covered from different upfronts. However, with KEDA, you can also have the ability of doing more complicated things. You can combine these scalars. And what is interesting here is that, of course, you can configure here and get the metrics from, for example, for Prometheus. And the typical case that I'm showing here is that you might be too aggressive on scaling out, but if that happens, if you don't take care of that, you might be actually causing problems to the database, for example. So there might be occasions where you actually, at some point, you might want to say, hey, hold on. I know that I have a problem and I need to scale out, but if I continue doing so, I'm gonna create more problems that I have today. So you can actually use the scale modifiers, and you can actually have formulas here that you can say, if the database write latency is lower than 100 milliseconds, stop, don't scale, or continue scaling, or keep it static. Right now, when the database is relaxed, I can continue scaling. So that's basically the benefits of using KEDA. What about Karpenter? Karpenter, we already know that is gonna write size, and the request that you send into the pods is extremely important, because that is gonna drive which compute capacity Karpenter is gonna launch. Too many people that is new to Karpenter think that it's basically about utilization, when it's not. It's basically about request, and basically the resources that Kubernetes is gonna have to guarantee that you have on the nodes. It's basically allocated resources, not utilization. And why it's important? Because Karpenter is gonna try to make decisions on choosing the lowest price instance possible. If it's gonna be on demand, in the case of AWS, it's gonna use lowest price, and if it's gonna be spot, again, it's gonna prioritize capacity, but it's gonna launch the cheapest available. The other things that we can do here with Karpenter, and maybe you are not aware of it, based on some recent features that we released, is that you can basically influence the schedule algorithm, the Kubernetes, the Karpenter algorithm and bin packing simulation that it does, and influence the instance type that you're gonna get. And of course, there are a few things that you can implement as well on bootstrapping the instance more quickly. So the first thing is that we released a few weeks ago node overlays, and this is basically an override that you can have on the certain requirements that you have in Karpenter. So in this case, you could say, like, based on the test that I did at the beginning, I noticed that Graviton outperformed x86, and I want to, of course, I want to have flexibility on using multi-architectures, but I want to give preference on a more recent generations of capacity. So in this case, it could be Graviton, or you could actually prefer to have latest generation before considering any other instance type. Because again, as I was saying before, otherwise Karpenter is gonna go with the lowest price available, and this is a way that you can influence that as well. So you can say, like, hey, the price adjustment, it's gonna be actually cheaper on this latest generation, even in reality, it might be more costly, but the price performance is going to be better for you. Then node overlays, it started as a price override, but it's also now in an AI era. You can actually influence and try to and tell Karpenter that that GPU node, in reality, instead of using one GPU, you can time slice it, and with the help of other schedulers on that context, now it's gonna use that and put that in practice. But this is a way of you can influence that. On the Karpenter side as well, it's a pretty easy trick if you are gonna be doing this for performance bootstrap. You can actually configure a RAID 0 on your disk. Different instance types in AWS have multiple NVMe disks, and if you want to make use of all of them effectively, you might have to use user data and configure all of that. Don't worry about that. You just have to use instance storage policy RAID 0, and with this containerd, and when you're pulling images, are gonna be using this disk, and it's gonna be faster. How can we increase that with such a parallel pull request as well? In a node class, you can actually configure this user data. We have a blog, we have a few blueprints that you can take a look. And the such a parallel pull request, it's basically a feature that it's gonna try to parallelize all the downloads of different layers at the same time of the container image. So we can see here that sometimes we've seen customers reducing 50% of the time of the pull when pulling large images. And maybe last but not least, we have, if you're using Bottlerocket, you can make use of data volumes. And what is interesting here is that you can use a snapshot ID that you can where you can pre-cache either container layers or a big model that you have, or even model weights if that's your use case, and do something like this. So effectively what it does is that we release a project where you can take a snapshot of the container images that you create. You can use that snapshot, and you can basically inject that snapshot at bootstrap time, and you can reduce the time very efficiently on this. And I want to show you here, I know I don't have much time left, but what I did here is basically, I actually put in practice this. This is the project that I mentioned before. I just basically pass the Docker image that I want, the disk size that I want, and it's gonna take a while, like 10 minutes on create this. It's gonna produce a snapshot ID here. So before that, the container image was taking almost 4 minutes, 8 minutes to get ready and pulling down. After that, it only actually took 44 seconds to pull down the image because the image was already there. So even though if your image is not that big or you're not planning on to, maybe this is an efficient trick that you can use on this. I'm not sure if you were not seeing that, right? This one?
I'm not seeing that.
Sorry about that. So this was basically, I thought that I was showing you this, but this is basically, you can see the events that were the previous pod that was not efficient was taking too much time, and this was basically taking 44 seconds, right? Of course, the idea was to show you this live, but I'm running out of time now. So just to close up, what I want to have a takeaway here is that scaling based on CPU memory is limited. Hopefully you can consider other types of scaling mechanisms. Instrument your applications from day one. It's pretty important. And I'm pretty sure that you might already have been using Prometheus. Take advantage of that, of those metrics. Continuous profiling with aperf. KEDA and Karpenter is going to help you to make this efficient autoscaling, but you have to do the job of right sizing, making sure that you are choosing the right instance for your workload. And as I was saying before, compute is only one angle. Think about storage, networking, and this is going to become even more and more relevant as we evolve into the industry with AI ML workloads. And yeah, 30 minutes was somewhat enough to give you an overview about this. So thanks for having me today. I'm going to be around if you have any questions.